5-7. So 5-7. And it's scale drawings, and models. And I kind of came up with like 3 types of questions you're going to see in these, so I'm going to do one of each of them in the notes. But first, kind of like, what are these things? What in the world are they talking about? So for a scale drawing, you could copy this. It's probably smart to copy it, but if you have a scale drawing, I don't plan to ask you the definition, but basically, what is it? A scale drawing, 2 things are going to be true. So one, it's going to be the same shape. A lot of respects, if you take a normal picture of somebody, that's going to be kind of like a scale drawing of the person. That it's going to be the same shape of them. Their head isn't going to be like smushed or stretched or something like that. It should be the same shape. They should look proportionally the same, but it's probably going to be a different size. So scale drawing, same shape, possibly different size. You could say usually, if you wanted to, different size.
Like our self-portrait.
Hopefully your self-portrait is the same shape. And sometimes when I do self-portraits, they do not look the same. But that's kind of what it is. Now, a big thing is going to be the scale. That if you have a scale of something, it's just going to be a ratio. And it's always going to be the model divided by the actual. Or it could be like, instead of the model, maybe like the picture divided by the actual, something like that. I'm going to put a big box around that, because that's important. You're going to get questions that say, this object here is this big in real life, its model is going to be this big, what's the scale, or something like that. Often, instead of it being written this way, you'll see it written out with a colon, so it would be like a model size colon to the actual. So I remember my brother made this sweet model of a F-14 Tomcat fighter jet when we were kids. I had the snap-together one. He had the one that you actually glue and paint, and his was way cooler than mine, and I was jealous. But it was like maybe like a 1:20 ratio or something like that. I don't know what it actually was, but if you have like, say, 1 inch, if it was 1:20, you could. I wouldn't write this. It probably won't make sense later. But if you have like a 1:20 scale, it's saying every 1 inch on the model is going to be equal to 20 inches on the real thing. Okay, so let's jump into like our 3 types of questions. The first one, I have a picture down here somewhere. I was lucky. That's what I got to drive from the wedding to the reception in. It's like, yes! And we took the long way. I got to drive it. Yep, it's only a 2-seater.
Don't you want to just like sit in?
No, I want to drive that. So that's the 1954 Corvette. Let's say you have a model of one of these. And let's say you have a 1:18 scale model. So 1 inch in the model is going to be 18 inches of the real-life car. Let's say the model is 9.85 inches long. So 9.85 inches long.
Wow, Emerson.
Then the question is, how long is the real car? So you have a 1:18 scale. The model is 9.85 inches long. How long is the real car?
Times that by 18.
Maybe. If we were to go through and say this 1:18, I could write that as a fraction, right? The 1:18 is the same as 1/18. And so if we have this then, the 1, that's going to be the model size, and the 18 is the actual, agreed? So if I want to make this into a proportion, 1/18 equals something with this 9.85. Does the 9.85 have to go in the numerator of the second fraction or the denominator? Numerator, because the 9.85 is how long the model is. So 9.85 inches. And then I'd have x be what we're trying to find. We're trying to find the actual. And you'll actually find that Abby was right in her way of doing it, because if you were to go through and cross multiply, you get 1 times x equals 18 times 9.85. So I end up with x equaling just the 18 times the 9.85. So 177.3 inches. It'll work if it's a 1 to something ratio, then it'll work. If it was instead like a 3 to 17 ratio, then when you cross multiply, instead of having a 1 right here, you would have ended up with like a 3x, and you have to divide by 3. But if you have a 1 to something ratio and they give you the length of the model, it'll work. So 1 to something ratio, they give you the length of the model. Any questions on that one there? Does that make sense? So those are going to be one of the types of questions that you're going to have. Sometimes, though, instead of giving you exactly the same, they'll give you a scale like this 1 to 18. Then they'll say the actual size is this, and you need to find the model. Enter the second example. Second example is kind of like that, but a little bit different. So I'm going to say for geography class, you're trying to do a map of the Appalachian Trail. So map of Appalachian Trail is 2,180 miles long. You guys familiar with that thing? It's a sweet trail. It goes from Georgia through like the backbone of the Appalachian Mountains up to Maine. So map of 2,180 mile trail on, we'll say, an 11-inch piece of paper. If you're trying to do that. Now the question we'll say is, what's the scale? So what's the scale? So if we were to go back to our ratio, it's always going to be the model divided by the actual. So 2,180 miles. Numerator, denominator? Denominator, because that's the actual length of the trail. So 2,180 miles goes in the denominator, the bottom of the fraction. And then the model, we can have a model be up to 11 inches long. So we have 11 inches in the numerator. Good? So you could say your scale is 11 to 2,180, but that's not really, that's not incredibly helpful. So what I would do is instead say, let's say we're going to do like a 1 to something model. So 1 to x. We could try solving that baby for x. We could say, okay, so I have 11 inches times x, so I have 11 inches. Maybe I'll leave my units off for now. I'm going to say 11 times x equals 1 times 2,180. Agreed? And I'm going to save a step and just say 1 times 2,180 is just 2,180. And so to get it by itself, I would divide both sides by 11. And then I come up with x equals, look here, so 198.18 repeating, which goes in there. So what we're finding then is, and maybe I should have up here said, our equation for a scale is saying scale is the model divided by the actual. So I have a 1 over 198.18 repeating. So that's like my scale, or I could write it as 1 colon, actually I should back up, or I could write it as, if I put in my units, so 1 inch over 198.18 miles. So I could write it as 1 inch colon 198.18 repeating miles. So that would work for an answer, but you agree that would be kind of an obnoxious number to work with?
Yeah.
So what you could do for something like that is you could do some rounding and say, all right, instead I'm going to have 1 inch equaling, if I want to fit it on the page, I could go up a little bit. So every inch, instead of being 198 miles, every inch could be like 200 miles. That would at least fit on the page a lot better. Or that would fit on the page, and it would be easier to work with. But you really could go with either one of those as an answer. Last thing, I want to go like definition-wise. I'm going to say similar polygons. So similar polygons. As this year goes on, we do a ton of work with polygons at the end. Polygons basically are going to be things like triangles or rectangles or squares or octagons. They're going to be objects that are enclosed that have 3 or more sides, and the sides are going to be straight. So if we have those polygons then, but they're similar, they have to be the same shape but maybe different sizes. So same shape but may be different sizes. So if they're similar, if they're same shape but maybe different sizes, the side lengths are going to make a proportion. So side lengths make a proportion. So side lengths make a proportion. Now I'm going to try to draw two triangles and try to make them look the same but have one be larger than the other. So this one I'm going to make a side direction about like that. Make another one that's about 1.5 times that length, call that 3. And kind of connect it. So that's my first triangle. Then I want to make a second one. Maybe we'll try to make it about 3.5 times as long. So maybe that side's going to be about 7. So make this one like about 3.5-ish times as long. So those are supposed to be my similar triangles. Hopefully they look kind of similar, and really they don't, do they?
One is just bigger. That's kind of the point.
Oh well, looks good enough. All right, so if we take this ratio of sides, do you agree on this first one? I could say, well, 2 over 3. If those sides form a proportion, I could take and make this equal to then this larger triangle. But if I do 2 over 3, what side has to go up here, my 7 or my x? 7, because 7 corresponds with the 2. Those are going to be the same spot. And then my x would be in my denominator. Now I could go through and solve for x in a couple different ways. One would be to, yay, so you could say 2 times x equals 3 times 7. 2x equals 21. And then divide both sides by 2. So those cancel out.
The 2 is on top.
Well, good question. Let me come back to that. So x then has to be 10.5. How do you know the 2 needs to be done in the numerator? It doesn't. You could do the same exact thing and say 3 over 2. I wouldn't write this. But then the x corresponds with the 3, so you'd have to put an x over the 7. If you go through and cross multiply and divide, you'll get the same answer of that there. Or you could even go 2 over 7 equals 3 over x and do it that way, and you still get the same answer. Any questions? All right.